So solids will dissolve if the attractive force of the water molecules is stronger than the attractive force of the crystal. So not everything will dissolve, if the attractive force in the crystal is stronger than the water, then it won't dissolve. In that case, the solids are called insoluble as opposed to soluble. So soluble, they will dissolve. If something's soluble in something else, they dissolve into it. If they're insoluble, they won't. Water can do the same things to polar molecules, and other molecules, polar molecules can do the same thing. Molecules that can hydrogen bond are extremely soluble in water. Water will not dissolve nonpolar molecules because they have no charge to attract the water molecules. So let's say this is a nonpolar right here, and this is polar. The water, there's no charge here, so they're not attracted to it. These guys say, not attractive. Why even bother? We're not even going to associate with these guys. And the nonpolar says, those charges are gross. We're not even going to look at those guys. So there's going to be no interaction between those with charges or partial charges and those with no charge whatsoever. The only interaction will be with other nonpolar molecules. I'm just making this thing up. They say, oh, I like the fact you don't have charge. That's attractive. So they are going to be attracted to each other. These polar molecules are going to go elsewhere or just stay to themselves. It's like, yo, gross, keep away. Nonpolar molecules are held together by dispersion forces, and nonpolar will dissolve other nonpolar because they attract each other the same amount as they attract themselves. So the same reason they're attracted to each other will be the same reason they attract other nonpolar molecules. Let's look at a quick definition of electrolyte. Now, a lot of people think electrolytes are these magical things that, oh, we need our electrolytes, we're out there playing a game and we have to drink our electrolytes, our Gatorade is an electrolyte, blah, blah, blah. But really, all electrolyte is a substance that conducts electricity when melted or dissolved in water. Salt water is an electrolyte. Lots of things can be electrolyte as long as they're ionic or polar. Conducting is charged pieces moving or electrons. Really just conduction is flow of electrons. Ionic compounds are electrolytes like salt water. They fall apart into ions that's able to conduct electricity when dissolved or melted. Now, non-electrolytes are substances that don't conduct electricity when melted or dissolved in water. Most molecular compounds, meaning those that are covalently bonded together, are non-electrolytes. They will dissolve because they are polar, and if they're non-polar, they won't dissolve in water. But they don't have to ionize to dissolve. They don't make charges either. There are weak electrolytes, substances that conduct electricity slightly when dissolved in water, just a little bit. Some molecular compounds are weak electrolytes. When they dissolve, they just somewhat fall apart and make a few ions, not so great. Don't make ions when melted. So an example, let's say someone's in a bathtub. And they think, well, you know, if I do an Epsom salt bath, I'll put a lot of salt in the bath.
And this is plankton, and that falls in. We have, whoa, electricity. This is going to be a pretty strong electrolyte. Conducts electricity. Strong. Got some salts in there and the water, it's dissolved. Flow of electrons is strong, and he's not going to be too happy. Whereas if you're taking a bath with just regular tap water has some dissolved minerals in it. It's not pure distilled water. You might be listening to his boombox in here, and it falls in. And this, he'll get a little shock there.
But it's not like the shock that he had when he had all that Epsom salt in the tub. Because water, even though it has minerals, it's plain water is just more of a weak electrolyte than water with a lot of salt in it. That would be a strong electrolyte. Hydrates, as the name implies, has water in it. Hydro. Ionic compounds that trap water in their crystal structure are hydrates. Now these are solid, and these powders have water. They might seem as dry as sand, but they actually have water in it. And it's the same number of water molecules. The number of molecules of water are written after a dot in the formula. For example, we have cobalt chloride, and there's a dot there with 6 water. This means that it's a hydrate. It has water in it, but it's not part of that chemical. It doesn't have anything to do with the cobalt chloride. Now the name, we use a prefix for the number of water molecules. Cobalt 2 chloride hexahydrate. So just know that if you see that solid, that powder has water in its structure. It's not part of the compound. It just has water in it. It might seem as though it's dry, but it has water in it. For example, a sponge might hold a whole bunch of water in it. You might think, oh, that's totally dry, but then you can squeeze it out. You just wring it out and it has water in it. It's kind of like the same thing. These hydrates, the water is somewhat hidden in it. Heating will force the water to leave. Now we've done this in lab where we've put some stuff in a test tube and we've heated it over a Bunsen burner, and what happens, this gets really dry, but then we get water molecules forming on the side, so we get a lot of water. We basically are burning that water out. We're heating the water out. I don't know what happened here, but that should be an arrow. We add heat, it goes this way. If we subtract heat, it goes back to the hydrate. So we take heat away, it'll become hydrate again. We force heat into it. That water leaves, does not want to be around. When water returns, heat released. Efflorescent hydrates will lose moisture to the air. Hygroscopic hydrates will pull moisture from the air. They're used to remove moisture from packages. Now, we've all seen these little tiny packages. They might be in vitamins or pills, or they might be in your a new purse you might buy. There's these little packets. They say do not eat on them. Those are hygroscopic hydrates that pull moisture from the air, because you don't want to get those vitamins all gushy with water from the atmosphere or the air outside. You don't want to get your nice Gucci purse ruined. A lot of times you'll go shoe shopping. Now you're going to buy some really nice expensive shoes. I mean, you might even go to Walmart. You really splurge on your shoes. Some nice high heel shoes, really fancy stuff. You want to put in that moisture packet, desiccant, that will remove moisture. So you see that a lot in stuff with like leather, and you don't want water to mess up. So it's going to suck that water from the air, and it's not going to ruin your new shoes or your vitamins or anything. Deliquescent hydrates will move so much moisture that they get wet themselves. Now soap has a very interesting property to it, and next time you're using your Irish Spring, this is what you think about. Irish Spring used to have those commercials where the guy would have a knife and cut open the Irish Spring and it'd be striped. It'd be pretty cool. But that's not the only cool thing about Irish Spring or soap in general. The cool thing about soap is what it does. It all has to do with the structure. It has a hydrophobic nonpolar end. So the end here, this tail, hates water. It's hydrophobic. Head here is hydrophilic. It loves water. It has charges. So we have a charged head and a hydrophobic tail. That's important how it reacts with water and oil. Here we have a dirt molecule or a drop of grease. Grease and water, what happens? Grease is nonpolar. As we know, oil, grease, you put it in water, it's going to stick together. It's not going to do anything with water. Water is polar. Soap will let you dissolve the nonpolar in the polar. So what happens is you have these hydrophobic ends that will be attracted to the grease ball. These ends say, ooh, nonpolar, I'm nonpolar, I'm attracted, like into like. The hydrophilic ends, these guys love the water, so they will dissolve in water. And what happens is these guys are attracted to the water, these guys are attracted to the grease, and all these water molecules are attracted to the heads of the soap. The tails of the soap are attracted to the grease molecules. What happens is if someone is showering or bathing and they have a lot of, let's say they just have some oil on their face, we'll get that Irish Spring, or this looks more like ivory. And this is what's happening. The non-polar parts are attracted to the oil on the guy's face. The polar parts of the soap are attracted to the water. So he's going to start showering, and that water is going to wash away that dirt because these polar heads are attracted to the water. The polar heads of the soap are saying, oh, take me with you, water. I love you, water. Whereas the tails of that soap are attracted to the oil on his face, and they drag the oil with them. And the oil says, I'll go with you, tail. I love the hydrophobic tail. So we can get rid of that oil. It just washes it away. Now he's a happy camper. Got all that dirt away from his face because the water was attracted to that hydrophilic part of the heads. The tail was attracted to the oil part, and it pulled away as the water washed it down. So water molecules can surround and dissolve the grease. Let's look at mixtures that are not solutions. Suspensions are mixtures that slowly settle upon standing. So they might seem like they're mixed solutions, evenly mixed, but if we just let them stand there, they will settle. Now the particle suspensions are more than 100 times bigger than that of a solution. So these are big things. And you can separate them by filtering. So examples would be paint, muddy water. See, that muddy water looks good enough to drink by my book. But if we let it settle, if we let it stand there, we're going to get settling. Some big suspension particles are going to go to the bottom, and it will separate out. The same thing with a paint. Colloids are another type of mixture that are not solutions. The particles are between the size of a suspension and that of a liquid. They're medium size. They won't settle or filter, but they're not quite small enough to be a true solution. For example, we have nice whipped cream or shaving cream and milk. These are colloids. The Tyndall effect is quite interesting. It's basically, if you put a beam of light through a mixture, such as either a homogeneous mixture, a colloid, or suspension, you will get a variety of results. You get either this, or this. It's reflection of light off undissolved particles. In a solution, you get no Tyndall effect. Can't see the beam. So if you go shine a beam of light through Coke, you should not. It should be a solution. If you get a beam of light, then you're not drinking pure Coke. You might be getting a suspension. That's where you get sparkle off of the big particles. Or you can have a colloid, which is a nice continuous beam. Let's take a look at this really neat animation. We go a beam through it, and nothing happens. That's a solution, nothing at all. How about a colloid? We got a nice continuous beam going there. And a suspension. Oh, look at those sparkly little lights. Very pretty.